casual Monday, so I just came like for the beach. But anyhow, so let's start. Our first speaker of the day is Stephan. He will be giving the tutorial. And once again, if you have any questions, please wave your hand and I'll bring the microphone to you. Please, Stephan.
I don't know, there are so many. Okay, I think now it's okay, right? Yeah, now it's working. Okay. Thank you. So, unfortunately, I'm not a member of the Swiss Roche family. Otherwise, I may not be here. Was so rich. Okay, so good morning, ladies and gentlemen. Actually, I have no words to express my gratitude to the local organizer and to Carlos, Sergio, and Yaro for giving me this opportunity to come in Natal and to give those lectures. So I think with Roland, we understood that there will be some students here, right? There should be my student, but I don't know where is she, in the beach, on the beach maybe? But I guess they are, right? Can you raise your hand if you are like student, or we have all experts? So 1, 2, 3, 4. Okay, so this is for you. Okay, but I will try to keep a certain level of entertainment for all the others, right? Instead of checking your emails, maybe you can enjoy some part of the presentation. Yeah. This one doesn't work?
I already got messages on myself
oh.
saying that.
Oh man. So, okay, that works? Okay. So we, together with Roland, we will try to cover, let's say, some basic concepts, background, state of the art, and also some very current issues in spin-based, spin transport in two-dimensional materials and van der Waals heterostructure. So we have a breakdown which consists first, I wanted to make a kind of very short overview about why we are happy to, why we think that two-dimensional materials are actually very interesting for spintronics application. And then I will present some kind of fundamentals of spin, dynamic spin physics in Dirac matter. We will have also a presentation about advanced concepts of spin transport. And Roland will cover experimental issues. We will also discuss valleytronics, optospintronics and optovalleytronics, which is very interesting, very specific to these materials. And we will have also very interesting presentation by Roland about 2D magnet, which is a new class of materials that are also extremely interesting in our context. So I'm coming from Barcelona, Center on Nanoscience and Nanotechnology, where we are studying a lot of different types of nanomaterials, nanoparticles, but we have half of the institute concerned and active in looking at graphene and other two-dimensional materials, because they have so many potential application that it's just fascinating. So my group is looking at the theoretical aspect of charge, thermal and spin transport in these materials and others. One characteristic is that we try to design some models that are as realistic as possible of the real materials that you measure, experimentalist. And then we use methods or high-performance computing in order to, simulate those realistic models and try to connect our result with the experimental data. So in the presentation of today, I will use a lot of materials, a lot of results produced in my group over the recent years. I also have to mention that I will not enter into the technicalities of some of the aspects of the methods that we're developing and we are using, but there is a general article where you can find the people interested all this information about these methods that allows to simulate systems like billion scale atoms when necessary. I also want to point out that this kind of presentation integrates a lot of ingredients from many collaborators, many collaboration we had in the past several years, and I'm very in-depth to especially people here, they recognize themselves, with whom I have enjoyed learning spintronic and having fun in studying a lot of problems. So, you speaking about spintronics, so this is the first slide in all the presentation we have is the start of spintronics, which is due to these two gentlemen, Albert from France, who first make this prediction that in this, when you have two magnetic materials and you interspace, you intercalate non-magnetic materials, you can tune the magnetoresistance of the junction by just changing the magnetization of the magnetic materials. And this giant magnetoresistance predict and confirm was not only awarded by the Nobel Committee, but also had a gigantic impact in magnetic sensors and non-volatile magnetic memories. So spin entered into the game at that time, and important observation, it was really, people say, the first application of nanotechnologies, because this layer could be made at some point, and it has to be in the order of the nanometers or below to make this kind of phenomena emerging. So for a long time, this memory application is the driving force of spintronics, but they have been concerned about why not going further and using the speed and degree of freedom to process information, to go for computing. So people, you have heard about the data DAS spin transistor, but new phenomena have been predicted and confirmed, and like the spin-Hall effect or quantum spin-Hall effect. And those phenomena are actually very efficient in order to move towards this manipulation of spin information. For a long time, one issue was, okay, you have a kind of contradictory aspect that you want to propagate spin information very long distance at room temperature, so being quite weakly, let's say, perturbed by source of spin orbit coupling. But at the same time, if you want to manipulate, you need spin orbit coupling. You need to act on spin. So these two aspects are kind of contradictory in order to have everything together, long spin transport and spin manipulation. The problem also is that metals and semiconductors do not really present the good figure of merits to move towards this new type of technologies. So from the very early days, graphene was identified by those people that I will mention now as really a new platform, unique platform for achieving those goals. Not only because of the very low spin orbit coupling in this sp2 membrane, but actually was soon realized that just having a kind of surface material, it could be very weakly perturbed, but you could strongly modify its spin properties. And this proximity effect turned out to be the key driving force towards everything that we will present with Roland and other speakers will present during this school. Initially, after the discovery of graphene, Bart van Wees reports the first paper where indeed they could measure by these non-local transport measurements, which are a bit unconventional in the sense that you have a current somewhere in your device, but you measure a non-local voltage away from the current flow, so this is not very conventional. But from this kind of experiment that I will explain by Roland, you can extract the spin diffusion length, the spin lifetime. And so this first experiment was very promising because 2 micron at room temperature was already one of the best figure of merit for any other materials. Albert Fert was immediately also interested by this. And a few years later, they report by a different technique on a different graphene, which was an epitaxial graphene, also apparently gigantic spin diffusion lengths at room temperature. We were a bit lucky in Europe because at the time very big initiatives were launched, known as the Graphene Flagship, and 1 billion scale, which is a huge budget, with the idea to bring knowledge to society, creating jobs. And among the list of applications that were identified by the experts, by the senior advisory panel with 4 Nobel laureates, we were lucky to have Albert actually pushing the consortium to consider spintronics as one of the very promising direction. So we have a consortium in Europe, a task force, which gathers most, not all, but most of the experts in the field, and there are a few here present, where we have been working for the past 4 or 5 years about trying to demonstrate that indeed graphene and 2-dimensional materials are really bringing value for spintronic application. On the way, we try to envision the roadmap. What can we expect in the next 10 years in terms of progress? What are the milestones? And actually, if you look at this, read this paper and look at this roadmap, the progress during the past 5 years have been quite aligned with what we expected, what we predicted. As I said, proximity effect turned out to be the key aspect, why such a materials could really have an impact in spintronic application beyond long spin diffusion lengths. This is one of also of the early paper we had where we started to look, and it was like it's a kind of 2 years work of DFT, relaxation. It's a gigantic amount of computer time to put graphene on a magnetic insulator and to see all this interface will actually relax, and all will be the impact of this magnetic insulator on graphene. What will be the size of the exchange coupling field, which will result in opening a gap, splitting the bands, and just showing that graphene becomes different, becomes spin imprinted by the proximity effect. Today, there is a race because the quantity of very interesting 2-dimensional materials is enlarging every day, and we are lucky because a person like Yao are very fast in showing the way somehow. What are the kind of materials combination, what are the kind of symmetries that can lead to a certain effect or another one. So the literature is exploding, but Yao is showing the way, and especially for us. This is an example of where this manipulation actually was demonstrated by our friends in Spain, where they were the first to put a transition metal decalcogenide on top of the graphene channel, making this non-local measurements, so voltage and current. This is a non-local resistance. And what you see here as a function of gate that is applied underneath is a switch on and off of the spin signal, because this non-local resistance is driven by spin information. So this kind of transistor of spin information, it's a speed field effect transistor. It was first realization on a graphene. This will be discussed by Roland, but the possibility to tailor the magnetism of these very ultra-compact 2-dimensional magnetic materials and to make vertical devices, ultra-compact vertical devices with gigantic tunneling magnetoresistance is just an achievement. And for memory technologies, clearly important direction to work with. Some people in France actually realized that coating magnetic materials with graphene or HBN will bring a very high value by reducing the current you need to use to switch the magnetization of magnetic materials that are used in the current MRAM technology. So this has an immediate impact, and is a case of study today to see how we can integrate these materials into spin transfer torque MRAM or SOT MRAM in order to demonstrate that higher performances. So there is the spin transfer torque, which is one of the principles of these new non-volatile memories, and for this spin orbit transfer MRAM, we have advances and a recent breakthrough by IMEC, who show that you can really large-scale integrate this type of memories for going to ultra-fast memories in maybe Internet of Things technology. So two-dimensional materials are offering very large possibilities to tune, to optimize all these properties, and this is some example of sketch where you can assemble them for a given goal. Beyond their horizons that people have tried to put forward, I think the first one was Roland about these magnetologic gates at room temperature, showing that you can encode with this non-local spin information some spin logic functions, spin gate. And then there are some spin orbit logic, theoretical proposal just published by Intel in order to use this for computing. Is a dimension, an extra dimension, going to the really quantum world of qubits, things like that. So it's just one slide to say that there have been early proposals. There are current efforts to connect two-dimensional materials with qubit technologies, and beyond the photonics also for manipulating spin. Then comes the valley, which we will discuss especially in two talks. The valley is another degree of freedom specific to this two-dimensional material. Not specific, but here it can be manipulated easily. And finally, I like so much this. This is really, for me, has been one of the greatest excitement. When I read your paper, Roland, where he showed, it was the first to show that you can connect photons to excitons. You create excitons in the TMDs, and then you transfer spin information that is dependent on the initial photon polarization. So this is a beautiful experiment, and is also opening a lot of new playground. Finally, I will make all this slide available, a list of the papers that have been personally used in this presentation. There is one which is particularly important here, Actas Physica Slovakia. This one is a key reference if you want to look at spin dynamics from a theoretical perspective. And promotion. We have a book, and we have a second edition where actually will appear early next year, where all what my presentation somehow is there in text. So let me start now entering into the world of spin physics in Dirac matter. First of all, I had to dedicate some time to briefly remind some aspects of the discovery of spin, which is so beautifully represented in a spinning top that you can move clockwise and counterclockwise. So, as probably most of you know, I mean, there was a Bohr atomic model was fantastically working for many species, but under magnetic field there was a kind of problem to explain some spectra. And that was in 1921, this experiment of Stern-gerlach was a major breakthrough in the sense that it reveals the existence of this internal degree of freedom of particles, sensitive to external field. Okay, where they have this silver atom, and then they have an inhomogeneous magnetic field, and so they could measure this splitting. So it was clear that there was something deep inside these new degrees of freedom, and as you know also, a few years later, Wolfgang Pauli, this giant of quantum mechanics, entered into the game and start to propose a theory to take into account these new degrees of freedom. 25, we have two group of people, Kronig and Uhlenbeck and Goldschmidt, that gives an interpretation. And all the intuition makes clear that this is an intrinsic angular momentum, and that makes all sense to think that this is because the electron is self-rotating, clockwise, up, counterclockwise, down. So they come with this idea. Uhlenbeck and Goldschmidt published the paper in Nature, but Kronig did not sign this paper, and these two persons tried to retract the paper before it was published, and they couldn't. And why? So Pauli came into the game. They sent the paper to Pauli, and Pauli had this argument. Guys, if you think that the electron is self-rotating, I will tell you this leads to a nonsense, impossibility. Why? Because let's assume that your electron is confined and is rotating, so you will have it will be confined to a certain sphere, which you can define by this classical Lorentz radius, which is corresponding to the energy to assemble the sphere of constant charge. Then you use special relativity to deduce these values, very small. But then your angular momentum, which should be quantized in the h bar, will lead to a velocity which is 70 times the speed of light. So that's completely doesn't make sense. And at the time, of course, quantum electrodynamics was not there. And so that's why people say, well, that's not the way. As you know, Pauli moved forward and found the mathematics subtleties of spin, degrees of freedom, and introduced these famous 2x2 matrices that turns out to describe the mathematics of what is really the spin. And these matrices are really related to the physics effect that will be sensitive to magnetic field. Of course, in this mathematical description, the general spin state of quantum particles is a superposition of up and down. So this breaks any possibility to envision self-rotating things in both ways simultaneously. So it just broke down this kind of intent to picture. Now, with this in hand, and let's go back to the Stern-gerlach experiment. So you send quantum particles like it's defined by a wave function. It has to cross an inhomogeneous magnetic field region somewhere. So for instance, you can put it like with a z dependence. And then you look at how the spin degree of freedom will evolve as your wave function cross this region. So you can decompose it into these bases, up and down. It's very straightforward then to introduce the Hamiltonian that describe the coupling with the spin and the magnetic field in homogeneous. This is a straightforward 2x2 diagonalized. The system is already diagonalized. You get the eigenvalues, the eigenstates, things like that. So what you can do then is to look at all the wave function, the spin part, evolve in time and in space. And since this basis is diagonalized in the z, you get immediately these two terms. So you have one component for the up and one component for the down. But it turns out that if you look at these two components, you will see that you have a kind of time-dependent effective momentum that is kicking the up spin on the top while it's kicking in space the down spin to the bottom somehow. So what does that say? That says that your probability to measure up spin, in one direction will increase in time, whether in the other spin population, its probability will increase in the opposite direction. So this inhomogeneous magnetic field is just separating up and down somehow. So this is a Stern-gerlach, but as we will see later, effective magnetic field like created by spin-orbit coupling interaction somehow playing the similar game. So in 27, Pauli published this theory, but at the same time there was this fantastic conference where Mr. Dirac, very young, was asked by Bohr, in principle, this is the legend, what are you doing, Dirac? Oh, I'm trying to take the square root of something. So, mysterious. So at that time, as you maybe remember, the problem was to find a relativistic form of the Schrödinger equation, which was so beautifully connected with classical physics by the correspondence principle between classical quantity and the quantum operators. And despite the attempts, the problem of generalizing the Einstein equation with the same ideas was leading to some problems. Taking a negative differential square root of a differential operator was quite ill-defined, or Klein-Gordon approach gave a negative density probability, which was also physically shocking. So, as you know, Dirac came with a fantastic idea to increase the space, degrees of freedom, and to define instead 4-component wave function to get a generalization of this equation, which end up into this beautiful Dirac equation, where it looks like the Schrödinger equation, except that you are in a higher dimensional space. You have the rest here, energy, and you have this sigma dot p, which makes the spin explicit, and the Pauli matrices. So your 4 degrees of freedom of the spin and the antimatter also came for free in this milestone of quantum physics. So now let's connect to our beautiful Dirac matter and graphene and so forth. So you all know that there is a nice linear dispersion between energy and momentum in graphene that we can derive from the tight bending model quite easily. So here you get Einstein and Dirac all together, with Einstein telling you, guys, if you have such kind of linearity, it means that you have an effective mass that goes to 0, quasi-relativistic, although the velocity is still far from speed of light. And then you have the form, this actually is the diagonalist form of this Hamiltonian, where you have the sigma dot p. Here, sigma is not the spin, but is pseudospin. Pseudospin, why? Because graphene has these symmetries which are specific. They only come with a sublattice degeneracy, A and B. You have 2 atoms in the unit cell. So actually, your wave function, where you look at the eigenstates, your wave function projects on the sublattice A, sublattice B. If it's all polarized on A, it's pseudospin up. It's all polarized on B, it's pseudospin down. And it turns out that the mathematical description is identical to the spin. That's why we call pseudospin. You can define, like in the spin, an operator where you get plus and minus 1/2, which define the helicity somehow of your state. And at the end of the day, what now you have to deal with is much more complex phase factors, because spin is there, it's moving on its own spin and processing depending on what is facing around, but pseudospin is also doing the same kind of dynamics, and you have to consider it. Pseudospin is something that has been really magic somehow. It has been shown that experimentally that you could measure pseudospin by polarization-dependent herpes, and we'll go a bit fast with that. Also, it has been shown that if the graphene is quite clean, this pseudospin can cancel back scattering probability in some circumstances, which was also a great achievement. And finally, for people who know about this weak localization, weak anti-localization, pseudospin rotates and can change when you rotate by 2 pi pseudospin phase. You get a change of the sign of the wave function, and this change of the sign actually can reflect in the change of the contribution of weak anti-localization in absence of any spin-orbit coupling scattering. And this was magnificently shown by these people, and also the theory was developed by Altschuler, Falco and company. So spin is moving, electron is moving with this internal degrees of freedom, and as you know, if there are environmental electric field, you can make a kind of base change, and in the rest frame of the electrons, there will be an effective magnetic field. So this is as the roots of everything. So this effective magnetic field will be sensed, probed by the spin, and the spin, some spin components will not sense it maybe, but others will start to processing around these fields, and so the dynamics of the spin components will start to emerge. Okay. Very important, actually, number is how fast do you process your spin can eventually process due to this effective magnetic field. So the spin precession frequency relate to the strength of the origin of this frequency precession is a very important question. There is one very important spin orbit coupling, which is a kind of illustrating essential features then for spin dynamics, is the so-called Rashba spin orbit coupling in a 2-dimensional electron gas. So the Hamiltonian is simple. You have this parabolic for free electrons, and you have this Rashba intensity with this symmetry. So you can rewrite. So it's a magnetic field that is depending on the momentum direction. So the bonds, this is very easy to diagonalize. So you have 2 bonds that are split by the spin orbit coupling thing and kind of momentum dependence. But what is extremely important is also the spin texture of the eigenstates. which turn out, if you look at the expectation value of the spin, to be completely locked with momentum. So they move together with the direction of the momentum. Spin momentum locking is what we use to refer to this very specific spin texture. And this is actually also the way to identify this effective magnetic field that can originate a precession of an inject electron with a given spin polarization. So understanding the value, the strength of this coupling is key to move forward. And first of all, I want to describe what was essential to achieve first is what could be the intrinsic origin of spin-orbit coupling in graphene. And thanks, as I say, we were very lucky that Jaroslav, Denis, Martin, they established a list of fundamental paper where they provide the overview of what's going on. So what's going on? We have mainly two important spin-orbit coupling origin. One, which is related to the atomic interaction between orbitals. And this gives rise to the so-called intrinsic spin-orbit coupling, which is complicated, depends on the type of orbitals that are in interaction. You can come out with a simplified low energy effective Hamiltonian, which actually tells you that this interaction is promoting a spin-conserving hopping process somehow between your electrons at second nearest neighbor scale, and it's opening a gap in your graphene structure. A gap which is small and give rise to it's very difficult to observe experimentally, but this is the length, the scale of the gap in the order of 20 microelectron volts. The second fundamental spin-orbit coupling is the so-called Rashba, which is a spin-orbit coupling that is induced by local electric field, which you can tune actually in your device. So at contrast to the intrinsic spin-orbit coupling, here it's scaled linearly with the intensity of the electric field. It has a different symmetries in the sense that it's flip the spin when you hop. And what is also very interesting that they report in the group of Jaroslav is when you look at the competition between these two spin-orbit coupling energy scale, actually you look at the bonds, you can see a very different results. Okay, you can have, as soon as Rashba is in the order of intrinsic, you close the gap, you still have a Dirac, massive and massless Dirac bonds in your system, which can evolve depending on the relative strength. So actually this bond structure then they have been seen in many different cases. And this is a kind of summary for people who like tensorial notation. It's beautiful. You put you have an 8-component wave function in graphene at low energy, so you have many tensorial products. What I want just to point out is, for the rest of the talks, is that these two type of spin-orbit coupling actually are giving rise to this beautiful spin transport phenomena, which are spin Hall effect and quantum spin Hall effect, that I will discuss in the second lectures. There is, however, an aspect that will show up in the spin dynamics, which I want to mention, is the fact, and it's actually general, this is the Hamiltonian written in their continuous form, is that when you get very close to the Dirac point, actually this part of the Hamiltonian, so this is a Dirac, a massless, this is a Rashba and the intrinsic. If you take your k going to 0, these are the terms that are dominating then the spin physics. It turns out that this is a coupling between spin, so spin will be the yes Pauli matrix, and pseudo-spin, which is a sigma. If you diagonalize your Hamiltonian, you would get this kind of eigenstate here, nearby the Dirac point. So I put an arrow for one and 1, 0 for the other, but I could put different arrows, colors, whatever. But what is important is that these eigenstates, you see that when you have pseudo-spin, let's say down, spin will be up, and vice versa. So it's kind of locking or entanglement between the spin and the pseudo-spin degrees of freedom. At very low energy, you have some kind of entanglement. Now let's go to the dirty limit, because that is also a very major issue in the devices that are measured. It's not super clean, flat graphene in the air. It's contaminated, disordered graphene on top of a substrate that is itself very disordered. So there are a lot of different sources of spin orbit coupling that can drive and completely dominate the spin dynamics and spin relaxation. For instance, if there are some metallic atoms on top of it, some initial calculation or experiments, they've shown that you get this kind of bonds. So this bonds exactly what I showed in previous slide. You introduce very strong Rashba or intrinsic and Rashba spin orbit coupling. So it's there, but it's due to impurity. So you have to deal with disorder in addition to this local spin orbit coupling field. So of course, one very key question that was really immediately addressed by theoreticians when graphene was found to have long spin diffusion is how long actually it will be when we will make our graphene super clean. So here I'm pointing out, I think, one of the initial very important work that actually showed the way. Again, produced by Yao. I hope you're not too much. So this was a very nice work, because it was the first where there was a combination between an homogeneous spin orbit coupling thing, Rashba type, and actually I think it's random, but disorder, impurities. So what was, as I say, what was done in this work, and what we one of the approach to look at the spin dynamics is to look at the spin block equation. All the spin evolve in time when you have this external spin orbit coupling field and the disorder and stuff like that. So what the author showed in this paper is that actually there is a spin relaxation, and the spin lifetime is very large. So what people expect as a density of impurity makes the spin lifetime in the order of microseconds or milliseconds. So this is 6 orders of magnitudes larger than what we had at that time, we knew at that time for other materials. So 6 orders of magnitudes is very large. And in addition, there was like a maximum of the spin lifetime when we were going closer to the Dirac point. So people try to progress in moving forwards, in trying to improve the quality and get the upper limit of spin diffusion lengths. So the quality of the various fabrication things are improved, the mobility raised to very large numbers, but the spin lifetime was kind of stuck to, let's say, 10 nanoseconds. And in addition, the spin lifetime was not maximum, but it was minimum at the Dirac point. So after dozens of experiments. The most recent result, which is extremely interesting for the community now, is this one published by Sergio's group and IMEC, who could succeed a systematic, very controlled fabrication of spin device with CVD graphene, which is scalable. And they found that the room temperature spin lifetime is in the order of a few seconds, and spin diffusion length 10 microns at room temperature. So it's like the best exfoliated graphene. So it was a real question, it's really confusing. What is the origin? What is the nature? If your system can be ballistic or diffusive and you get the same numbers. So that's being a lot of controversies and discussion in the literature. So there are 2 mechanisms that are driven the loss of spin information, which are actually so opposite. So very nice. One, which is the fact that your spin experiences scattering, bouncing off an impurity, which rotate the spin, like mixture of spin up and spin down. And this means your spin information relaxing faster if you have more of such scattering. And you have another one, which is actually very beautiful, which is the spin lifetime is just driven by the precession of the spin and interference and dephasing. But when you have a scatter, you just improve the spin lifetime. So the spin lifetime is actually inversely proportional to the scattering time introduced by impurities. So that's more counterintuitive. And this is actually what happened. Here you have a kind of cut of your Dirac cones. You suppose you have your spin line in one direction at time 0, And what we do here is just to put a certain probability to scatter at a fixed energy. So here we just have two conditions. The first one, the spin precession frequency is actually, the spin precession time is actually much larger than the scattering time. In the second case, the spin precession time becomes in the order of the scattering time. And you see, this is what we have in time, what happens to the population of spin all around this circle at a fixed energy. So you see there is a big difference. Here you see that you see your spin start to precess. In this case, at the same time scale, they don't. They are just like locked to the upper direction because scattering prohibits, block the precession. So then you look at ensemble average of all the polarization change in time, and you will see that in this case, your polarization is maintained for much longer time scale than in the other case, faster. So that's the so-called motional narrowing, and that's explain these kind of things. The faster are these things, the longer will be the spin lifetime. So in graphene, this has been tried, people have tried, but it turns out the situation to be very complicated to realize what do you fit with that, or you extract the mobility, and just if you look at this paper of Barber and Weiss, we don't really know. We can fit with different parameters. Please, guys, give us some hints. In this experiment in Germany by Bernd Buchner and Christoph Stampfer, they tried to make a statistics of devices depending on the quality of the device, and somehow they achieve for most of the device, actually the ones that are more disordered, deposit on silicon oxide, a trend which is going to this Dyakonov-Perel. The cleaner the system, the shortest the spin lifetime. Well, in graphene deposit on HBN, it became a bit more fuzzy, somehow, more clear trend and question. So one of the key questions was, okay, we really need to get an answer to that. We're just stuck, we cannot improve in the experiment, or we have completely contradictory results concerning the quality and the resulting figure of merit. So what's going on? So we have to combine very short spin orbit coupling strength with the disorder that is specific to graphene deposit on a substrate. And this you can really achieve this information extremely realistically somehow. Okay, but before I'm showing what the simulation, the brute force simulation is providing, there is an important thing that I mentioned, this Rashba spin orbit coupling field where everything is under control. When you put disorder, there is a very specific fingerprint of this Rashba spin orbit coupling field, which tells that and this is in the review of Yaroslav, which tells that actually you can get an analytical form, more or less, of the spin lifetime with the scattering time and the spin orbit strength. But there is something that is always there, that the out-of-plane polarization, so your Rashba is in plane, will be 1/2 of the in-plane spin relaxation. This is something you can derive analytically. It's there. Rashba in plane plus disorder, strong disorder, spin momentum scattering time shorter than the spin precession time. You get this. You get 1/2. You don't get anything else. So here I showed, I will go a bit fast, full simulation of the spin dynamics, where we use a description of the disorder, which is of these electron hole puddles, because graphene is deformed, which is very realistic. And actually, when we compare graphene on silicon oxide and graphene on boron nitride, we find that we are in two different spaces. One where indeed we are in the Dyakonov-Perel regime that I mentioned before, and the other one, we are not in this regime. We are in another thing, the spin precess more before it scatters, because of the cleanness of the substrate. So this is kind of movie where, let's see if I can make this working. No, I can't. Maybe I click here. Yeah. So there is a spin at time 0, which is, or maybe the movie is difficult to. Yeah, the spin is injected in the center of a grain boundary, and then it precesses with an in-plane Rashba. So you see red, blue, because you do that, you precess. But then all the spin information moving in all direction, and you lose the information. So you can do this with this type of brute force exact track of the spin polarization, spin expectation value. And what you get for this type of substrate is, in the case of boron nitride, you see this oscillation. So they precess before they relax. Whether on silicon oxide, the relaxation doesn't show any fluctuation. So from the numerics, actually, you can fit, and you get the spin precession time, and you get the spin relaxation time. Now, if you report what you get numerically for the graphene on silicon oxide, and you extract the spin lifetime, you have this Dirac-Perel regime. You're exactly in this regime where I think the spin lifetime increase with the density of defect, and the ratio is 1/2. When the system is cleaner and you have more oscillation, it turns out that you can still extract these values, and these are reports, and compare with silicon oxide, and you get a very large difference, but close to the Dirac point, strangely, the difference is not that strong. And if you take values of the Rashba that are actually very small, like 4 or 5 micron EVs bottom, if you put 0, spin lifetime is infinite. But if you put 5, you get these numbers. Sounds like what we have in the experiment. And it turns out that the mechanism that explains that is nothing to do with the conventional mechanism, but has to do with what I said before, that spin and pseudospin become entangled at the Dirac point. So entanglement of different degrees of freedoms is expected to also contribute to the spin dynamics. The things cannot be, deconvoluted. Actually, this is what we show, that when you are far away from the Dirac point, your two dynamics, spin and pseudospin, in a system where you have weak disorder, they are decoupled. But when you get closer to the Dirac point, things are completely entangled, and the dynamics are completely different. And this expressed, in particular, with the spreading in energy of the spin precession frequencies, which is actually the key element to understand why at the Dirac point spin relax faster. So these are, for instance, high energy, your pseudospin dynamics is just very fixed to a single precession, but if you go close to the Dirac point, you have a strong dispersion, changing a little bit your energy because of its entanglements with spin, degree of freedom. Okay, so we went a bit more into the detail, and really the very important point is that the spin precession frequency is not constant in energy. That's the key difference, which is unveiling all the entanglements reflecting the dynamics, and which explain what is minimum at the Dirac point. Actually, we found also something, and for a time nobody could measure that there was a downturn at high energy where pseudospin entanglement was lower. But actually, we mentioned that if you look into your low energy spin orbit coupling Hamiltonian, and you add extra terms, high order terms, then this downturn is found. If you get rid of this extra term, then you just have an increase of the spin lifetime. And I just mentioned that in this work of Sergio, for the first time, we have the faith to see that something like that was observed finally. Okay, let me forget about that. So we have two kinds of mechanisms, which are very different and depend on the quality of the materials. However, it turns out that methods was developed, will be presented by Roland, I think, in order to probe this spin transport anisotropy. And very careful work of Sergio's group for graphene on boron nitride and graphene on silicon oxide did not lead to 1/2, but just 1. So isotropic spin relaxation time, which is incompatible with Dirac-Perel and strong disorder. So we need to think about an additional source of spin relaxation. Jaroslav, again, proposed these magnetic impurities that will be the source. Let me forget about that. Time. So one of the key questions also we had is why spin diffusion length seems to be insensitive to disorder. In polycrystalline graphene, they found recently 3 nanoseconds. And during 1 decade, people thought for exfoliate graphene to be super clean, and they got the same value. And CVD is very important because it's scalable, because you can do it at that scale. So for application, it's essential to understand the role of grain boundaries and the average grain size on the spin diffusion lengths. You need model, but you can design those models very realistically. And one of the key questions is, how my spin diffusion lengths will scale if I'm increasing the average size of my grain? And that's a very key question, because if you want larger single grain, it costs a lot of energy. So we work a lot, and the group of Jean-Christophe come out with a very kind of general, universal way, a type bending model, in order to take into account all these non-hexagonal rings into a disorder graphene sp2. So I have no time to go into the details. I will go fast. We have a model, so then we can compute the spin dynamics with the same type of approach and see how the spin diffusion lengths change with increasing the average size. And what we found, actually, we forget about that. I plot the spin polarization as a function of mean square displacement. And actually what we found is that the relaxation is only driven by the strength of the Rashba spin-orbit coupling. It's not depending on the average grain size. So I can have 10 nanometer mean free pass, I can have 1 micron mean free pass, I will get 10 microns if I have 20 micro LeV of my Rashba, or I will get 50 micron if I have 5 micro electron volt. So that's very interesting result for pushing to technology. But actually it's a trivial result if you are in the Dyakonov regime and you have this disorder, because you get this in 2 equations, you get the value, you get this. And this is in the review of, probably is in the review of Jaroslav. So I'm going slow, but I want to touch upon this topic. All this proximity effect, you put now graphene on top of whatever, you get something very important. And one of the most exciting interfaces is graphene on TMDs. Because of this symmetry of TMDs, there is a good kind of isomorphism. And so you can rotate the angle, of course, but so here again, one slide, same people, extremely important, doing DFT, very accurate way, extract all this interaction, split the bonds, introduce new spin-orbit coupling terms. So there's a lot of work. I think this is with Denis, Martin, and Yao. And very essential information is what is the spin texture of the state. I said the Rashba is in plane and like winding this way. They found that because of the complexity of the symmetry, there are out-of-plane contribution that's there. But beyond the DFT, they also elaborate the models to extract what are the origin of all this spin effect. And beyond the Rashba, they also identify additional symmetries and additional terms that were essential to capture bounds and spin texture. And actually, if you compare what you have in the conventional Rashba here, spin texture, I want to show this one, this kind of winding spin texture, and you compare what you have on graphene deposit on a TMD, you get something really strong here, an out-of-plane polarization that is very strong, in addition to the Rashba. But you get this out-of-plane polarization explained by a kind of Vallée-Zeeman, so it means that spin texture is up or down for these 2 time reversal valleys. And it turns out that when you do the simulation, you want to do what will be the spin dynamic in such a system, we could find that the spin anisotropy is not 1/2, but it's 10 or 11. So that's gigantic difference to, let's say, a conventional 1/2 in the Dyakonov-Perel regime. So this giant anisotropy is related to this spin texture and the fact that you need disorder actually to get this. You remember what I showed, this Dyakonov-Perel, that I was putting a lot of scattering and my spin were just fixed outside. So here you have a magnetic field, effective magnetic field, which corresponds to the spin texture that force my inject spin. If my inject spin is out of plane, it will not process, it will be completely blocked. So that's the explanation. Whether it's inject in plane, then it will process like hell and it will relax. So there is a possibility to derive this analytically, and also I want to mention that Aires Ferreira has really extended all the theory to get purely a rigorous formula. That's you can see where are the origin of the anisotropy, and there will be an explanation about the experimental investigation of that. So I don't know what to do. So concerning all the materials like graphene topological insulator, I want to go very fast. It's very interesting materials, three-dimensional materials. So when you start to hybridize graphene on top of a TI, you get a structure that is very complex, actually. You have some kind of charge transfer, so the bonds are shift in the bonds of graphene as the Dirac point is shift in the conduction bound of the topological insulator. The surface that is in contact with graphene also is symmetry is broken between bottom and top surface, so that's why you have a splitting of the Dirac cones of the topological insulator. So, etc., etc. So again, the same kind of work has to be done at DFT, type banding, and again, the spin texture is really important. And what you find, again, in this case, the spin texture out of plane is very strong, and the Rashba actually disappear when you get closer to the Dirac point. There's a small gap, let's say the Dirac point. As a result, depending on the type of angle, actually, your spin transport anisotropy can change very, very strongly. So here, for instance, you have a gigantic increasing close to this Dirac point. In this case of the angle, it's different, or you can completely switch off with another angle, and there is no anisotropy. So this is all this twisting and physics change with twisting illustrate in this type of interface. And I think maybe Roland will show a very nice on the bilayer with a magnetic field, bilayer with an electric field that can tune the gap. So I have 4 minutes. Yes, we can stop. We start the questions. Okay. As you wish. Whatever question about.
So what you showed this. Can you go back maybe one or two? Yeah, this one.
This one.
So what is the difference? What is the analytical result that you have on that? How is it?
There is the faith of ab initio, and the fact that we can identify, the origin of this, the spin orbit coupling terms that are at the origin of this anisotropy. But there is no. In this case, there is no. Maybe we can do that, but that's not.
No, I'm just asking. You have analytical. There's no expression.
No, okay, you're right. Sorry. So there is maybe a formula somewhere. No, it's not in this slide. Yeah, we have to compute. In this case, to compute the anisotropy, we have to assume, because this is purely DFT, we assume that there is disorder that created a Dyakonov-Perel. So we need scattering in the system. Otherwise, there will be no anisotropy.
And then you use the wave function.
The analytical.
How do you calculate this? Well, I don't really know what the analytical means there.
No,
just using like Concham.
Sorry. Now the analytical is, I think the analytical means probably, we have made some kind of similar to the graphene on TMDs, and in some circumstances we can have some analytical form. Like I say, for graphene on TMDs can be derived. But there is no real surprise. And then, but for the purely DFT or TB, there is no real disorder in this calculation. We assume that there is additional disorder, we are in a Dyakonov-Perel, and then we can extract an anisotropy. Without disorder, there would be no anisotropy.
But the disorder is not really in the DFT calculation.
No, it's not. Yeah. It's not. Okay. So this is a very new, I think even not even published by people in Aachen, where they put graphene, they embed graphene in between boron nitride, encapsulate, and tungsten diselenide. So there is a strong spin orbit coupling effect, but the system becomes ballistic. So what about the spin diffusion in the system? That's a real question. What happens? And that's I don't have the answer. I just show what we would like to do. So in order to extract the spin diffusion, this will be covered by Roland, so I will not enter, but you have mainly two approach. You have a way to scale up your device measurements and to change the channel length. So when the spin signal relax, because of course spin information is lost, you can extract from your relaxation length the spin diffusion length. Or you can just have one device, but you put an external magnetic field to monitor the dephasing, and you can also make a theory with a spin diffusion equation. So you can fit your experimental data and you get this spin diffusion length, spin lifetime. So the problem is that this derivation and this analysis of the data by the spin diffusion equation suppose several approximations. First of all, that the spin actually really scatter. It's really scattering like this Elliott effect. And usually the complexity of the device geometry is not taken into account in the spin diffusion equation, or it's at a very phenomenological level. So in order to address this problem, you can do that by the brute force simulation of the non-local resistance by using this multi-terminal Landauer Büttiker. So what we did in this study is that actually we did something that is clearly possible in real life, is that the origin of spin rotation has nothing to do with the origin of charge scattering. Okay, it's very nice to see the electrons with the spin processing and tack is scatter on each end and tack is scatter, but this is okay, can work in some situation, but it's not general. There's no reason. The complexity of the spin, the interference makes the situation. So you can have a source of spin rotation. For instance, this is an homogeneous magnetic disorder that changes the spin degrees of freedom, so the spin will precess in its Bloch sphere, but it's completely disconnected what happened in the charge. Momentum scattering has nothing to do. So we can play with the Hamiltonian and Anderson and this type of magnetic disorder. And then if we want to connect the simulation, then the simulation, want to see how to interpret the simulation, we need an extended theory which take into account this additional device related effect. And we can make a brute force simulation. This is what we did. And this is an example. So we have the non-local resistance as a function of channel length of the system. Okay, but in this situation, we are like, mean free path is just smaller than the channel length. But even though what we found is we fit our numerical data by the conventional formula, and we see that when we have low magnetic disorder, so spin becomes more and more ballistic, so to speak, this conventional formula just underestimate what we get with the more general formula. Okay. Actually, the more general formula can also explain why you become linear at some point. So it's impossible to fit a linear curve with an exponential. You get a value that you cannot really control. Actually, this linear behavior in the very, very low spin, relaxation or spin diffusion limit is actually captured by the generalized formula. So you can do the Hanley also, so you can put the magnetic field and you can have this modulation of the non-local resistance as a function of the magnetic field, so you can do the fit and do the same, and you get, obviously, the same kind of trends. But what you can do with brute force, let me finish please, and I answer the question, this is the last slide. When you do with the brute force, you can play with the parameter and then so you can enter into this unknown zone where spin do not rotate at all, but charge neither. So you have a ballistic transport, you have a spin that do not rotate, but you measure something. And if you have a magnetic field, you can also force the spin to precess and so forth and so on. So these regions of quasi-ballistic transport of spin is a region that you can investigate numerically. And you can, this is a nanoribbon structure, so there are additional issues, but let's say that you can move on to generalize the theory in this regime, which is achieved today in the experiment. So I think this is the last. So thank you very much for patience, and let's see if you want to start with the question. Let's just start. Thank you. Thank you.
Yeah, can you go back to the model?
The first one? Yeah. The model?
Yeah, the model. How do you connect this, the Hamiltonian and this, the non-local resistance, the non-local resistance? Are they connected? Because I'm familiar with this kind of formula when